Greetings, ladies and gentlemen, and thank you very much for accessing this presentation of the SA Powertrain Fuels and Lubricants paper entitled Fuel Effects on Regulated and Unregulated Emissions from 3 Light-Duty Euro 5 and Euro 6 diesel passenger cars. My name's Rod Williams and I'm presenting this work on behalf of Concawe. This slide shows an outline of the presentation. So firstly, I'll give some background, then the objectives and scope of the study, then some key details of the experiment. I'll talk about the results based on the tailpipe emissions, then the results comparing the engine out and tailpipe emissions from the Euro 6D temp car, and then some conclusions. Firstly, some background. So European automotive vehicle technology and fuel technology has advanced in parallel over the last few decades to reach the level where we are today. Further advances in pollutant emissions will probably come into play in the next decade or so with Euro 7. But meanwhile, the emphasis is changing to reducing the global warming impact of vehicles, and this will drive us both vehicle efficiency and a shift to more renewable fuels and electrification going forward. Fatty acid methyl esters are the most abundant renewable fuel suitable for use in current technology compression ignition engines. It's permitted in EN590 up to 7% volume and up to 30% volume for some captive fleets and in some non-European markets. FAME has potential to help further with the switch to renewables, but with it comes some challenges around indirect land use change as well as vehicle compatibility. Renewable paraffinic diesel, such as hydrotreated vegetable oil, faces some of the same ethical challenges around ILUC, but brings some benefits in vehicle compatibility and pollutant emissions. And there is a wide range of alternative renewables transport fuels that are at various stages of research and development. And now the objectives and scope of the study. So the study objective was to provide some understanding of the benefits that diesel fuels can provide in current technology applications in both terms of emissions affecting local air quality and in greenhouse gas emissions. The scope of the study is there's a focus on tank to wheels, greenhouse gas and pollutant emissions effects. Some fuels tested weren't EN590 compliant, and so vehicle compatibility considerations were outside of the scope of this study. Tests were run over the WLTC rather than the RDE protocol, so that we could obtain the experimental repeatability required to analyze fuel effects. And testing was limited to one example each of a Euro 5, a 6B and a 6D temp European passenger car due to resource constraints. And now an overview of the important experimental details of the study. This table gives an overview of the fuel set used in the study. So fuel 1 is an EN590B5, where the 5% biodiesel is from used cooking oil methyl ester, so a waste-based feedstock, and the balance is a conventional European diesel stream. So this is a comparator fuel and also acts as a blend stock for some of the other fuels. Fuel 2 is a low-density B5. Again, it contains the same 5% Eucomi, and then the conventional component is from lower density streams that are typically found in jet and diesel. So this gives a lower density, higher hydrogen to carbon ratio fuel. And then fuel 3 is a paraffinic diesel fuel, in this case a renewable one, so hydrotreated vegetable oil, and the paraffinic diesel fuel represents various sources. So this is characterized by having very low density, high cetane number and low aromatics. Fuel 4 is a 50-50 mix of the paraffinic diesel fuel and the EN590 B5 fuel 1. And this is to investigate the impact of PDF as a blending component. Fuel 5 is a B30 fuel, again with the biodiesel component is Ucomi, and the 70% conventional component is the same as used in Fuel 2. And Fuel 6 is the B30 used in B5, but with a high dose rate of cetane number improver. And this is to investigate if the cetane number improver will counter any NOx penalties. So the fuels are evaluated in two subsets. The first subset is the low density fuel set, where fuels 2, 3 and 4 are compared to fuel 1. And the second subset is the B30 fuel set, where fuels 5 and 6 are compared to fuel 2. This slide shows some details of the test vehicles. The test vehicles were chosen to represent vehicle types which are common in the European market, to have engine and emission controls technologies which are common. We wanted to vehicles which spanned Euro 5, 6B and Euro 6D temp. The vehicles are from different parent OEMs, and common car segments and engine sizes are represented. So a key difference between the vehicles is in the exhaust aftertreatment systems, and this is illustrated in the diagrams on the right hand side here. So car A, the Euro 5 car, uses high pressure EGR, diesel oxidation control catalyst, and a coated diesel particulate filter. Car B, the Euro 6B car, uses high pressure EGR, a lean NOx trap and a coated diesel particulate filter, and passive SCR. And car C uses high pressure EGR, a passive NOx absorber, urea SCR, and a combined SCRF ammonia slip catalyst unit. This slide shows some details of the testing. So tests were carried out over the WLTC. Road load models for the vehicles were derived from track-based coast downs. Test order was designed to avoid back-to-back repeats on the same fuel, and the overview of the test order is given in the table at the bottom of the slide. Between tests, fuel was flushed and a full WLTC cycle was driven as a preconditioning step. And vehicles were soaked and tested at a temperature of 23 degrees C. Tests affected by DPF regenerations were rejected and repeated to ensure we could maximize the potential to detect any between fuel differences. Key measurements made are summarized in the table on the right hand side of this slide. Physical parameters as well as some parameters via the onboard diagnostics were recorded to ensure consistency between tests, including critically EGR level. Regulated emissions were measured, as well as some non-regulated emissions which are slated to come into force in future generations of European legislation. And engine out emissions were compared to the tailpipe values in the Euro 6D temp car. So now a summary of the tailpipe results. So this slide gives both an overview of a key to how the results are displayed in the coming slides, and also the CO2 tailpipe results. So you can see the color coding used for the different fuels, and in all the charts shown, error bars denote the 95% confidence interval about the mean. Differences between fuel means that are statistically significant at the 95% confidence level from the relevant comparator fuel are marked with patterned bars. So in the low density fuel set, you can see that fuels with lower density and higher hydrogen to carbon ratio tend to give lower CO2 emissions than the EN590 B5. And in several cases, the PDF 50 fuel gives a disproportionately high benefit. In the B30 fuel set, the B30 with and without cetane number improver gives a variable impact depending on vehicle, and this could be due to differences in individual vehicle calibration. Fuels with lower density tend to give higher volumetric fuel consumption, and this would be expected due to the lower energy content on a volume basis, but they give similar energy consumption, and there's just one exception there on the energy consumption side, where PDF gives higher energy consumption in the Euro 6D temp car, which again could be a peculiarity of the vehicle calibration, or even just an erroneous result in that case. Fuel and energy consumption is unaffected by B30, but the effects of B30 plus cetane number improver in two cars, again, could be calibration specific. They're actually in opposing directions, so this could be due to different sensitivities to combustion advance with a high cetane number fuel. NOx from the Euro 5 car was substantially over the Euro 5 limit, albeit that the car would have been certified over the NEDC, not the WLTC. NOx from the Euro 6B car was close but still above the Euro 6 limit. Again, that car would have been certified over the NEDC. Whereas NOx from the Euro 6D temp car was under the Euro 6 limit in all cases. As well as fuel effects on NOx, fuel effects on the fraction of NO2 were examined, and there were no significant effects of fuels. That data isn't displayed here, but it's available in the appendices of the paper. So for the low density fuel set, NOx was directionally lower with the low density fuels. However, this was non-significant. On a fleet average basis, the benefit for the paraffinic diesel fuel was statistically significant. In the B30 fuel set, NOx was significantly higher with B30 and also with B30 plus cetane number improver in the Euro 5 car, where the NOx was very high in terms of absolute levels. These signals weren't apparent in the data from the Euro 6 cars. The addition of cetane number improver to B30 didn't reduce the NOx values in any car. Particulate mass was very low for all measurements. It was less than 0.4 milligrams per kilometre in terms of all fuel means, and there were no significant fuel effects. The data is not displayed here, but it's available in the paper. Particle number means for all measurements were below the 6 times 10 to 11 Euro 6 limit. And in terms of fuel effects, there were no significant fuel effects on PN in the low density fuel set under any measurement size range. So as well as those illustrated here, we also took measurements in the size range from 4 nanometers up. The B30 plus cetane number improver fuel was the only fuel that produced a signal in this B30 fuel set, and it was only in the Euro 6D temp car. The signal was present in all size ranges and measurement methodologies, but it should be noted that only a single valid measurement was captured on B30 plus cetane number improver fuel in the Euro 6D temp car. So this may be a real signal, or it may be an artifact of the measurement. Carbon monoxide tended to be very high in the Euro 5 car and also quite variable, whereas it tended to be very low from the Euro 6 cars. In terms of fuel effects, the low density fuels tended to give reductions in CO, but only in the Euro 6 cars, and the PDF 50 fuel gave disproportionately high benefits in this case. In the B30 fuel set, CO were tended to be lower for the B30 and B30 plus CNI fuels in the Euro 5 and Euro 6D temp cars, but not by a statistically significant margin, except in one case in the Euro 6D temp car. Hydrocarbon emissions were very low across all fuels and cars. Hydrocarbons tended to be lower for the lower density fuels, and proportionally this difference was higher for the PDF 50 fuel. There's no impact on hydrocarbons with the B30 or B30 plus cetane number improver compared to the low density B5 that was consistent between the vehicles or statistically significant. Ammonia emissions were very low in the Euro 5 and Euro 6B cars, but higher in the Euro 6D temp car, which has urea SCR. There were no fuel-related differences detected in the results in either fuel set. Methane emissions were vehicle dependent and highest in the Euro 6B car, which has a lean NOx trap, which is regenerated by rich fuel spikes. Unexpectedly, nitrous oxide wasn't higher from the cars with catalytic DeNOx systems. And it's possible that the atmospheric nitrous oxide has contributed to the tailpipe levels that we measured. In terms of fuel effects, the low density fuels tend to reduce methane, similar to those trends observed in hydrocarbons, but to a lesser extent. And the low density fuels tended also to reduce nitrous oxide, with some of those differences being significant. Again, trends in methane with the B30 fuel set were similar to those seen in hydrocarbons. And there were no differences in nitrous oxide that were significant or consistent between vehicles in the B30 fuel set. Carbon dioxide, methane and nitrous oxide emissions were added to determine the total greenhouse gas emissions for each fuel and car combination, expressed in terms of the global warming potential, 100-year figures using the Greek model. The global warming potential of the methane emissions measured in this experiment were between 0.06 and 0.6 grams per kilometre CO2 equivalent, and for nitrous oxide they lay between 1.6 and 2.3 grams per kilometre CO2 equivalent. In terms of fuel effects, the results showed significantly lower greenhouse gases in most cases for the low density fuels. And in 8 out of 9 cases, the total greenhouse gas differences were larger than the CO2 differences. Greenhouse gas emissions on a CO2 equivalent basis showed little difference from the CO2 results in the B30 set. Now a comparison of the engine out and tailpipe emissions from the Euro 6D temp car. Tailpipe CO2 levels were slightly lower than engine out levels. This was unexpected. The expectation would be that tailpipe levels would be slightly higher due to oxidation of carbon containing species over the aftertreatment system. And this difference is attributed to the different measurement methods used for the engine out and tailpipe measurements. Trends in engine out CO2 were similar to those of tailpipe CO2, though engine out results are more variable. Engine out NOx is substantially reduced across the exhaust aftertreatment system, as would be expected. Emissions from the low cycle of the WLTC, including the cold start, are similar to those from the whole WLTC, though tailpipe emissions are substantially higher, and this difference is due to the aftertreatment efficiency related to temperature. Fuel effects are similar between the low subcycle and the whole WLTC. They're not illustrated here, but they're available in the paper. So in terms of fuel effects, engine out NOx tends to be lower from the low density fuels. Therefore, lower conversion efforts are required for the after-treatment system for these fuels. Engine out NOx from the B30 and B30 plus cetane number improver is significantly higher than for the low density B5. However, these differences aren't significant in the tailpipe emissions due to the efficiency of the after-treatment system. Carbon monoxide from the engine out and tailpipe are shown here, both in the left-hand charts from the low cycle, which includes the cold start, and in the right-hand charts from the whole cycle. So engine out CO is substantially reduced across the exhaust after-treatment system. Carbon monoxide from the low cycle is higher than the whole cycle, as would be expected. Low density fuels tend to reduce engine out CO, except apparently in the case of the low density B5 as circled. This could be an artifact of the measurement, given that a benefit is seen in the tailpipe CO and yet not in the engine out emissions. Benefits are proportionally larger in the low cycle results. B30 tends to reduce engine out CO. Cetane number improver increases the benefit, and benefits are proportionally larger in the whole cycle results. So an opposite effect to what we see in the low density fuel set. Hydrocarbon levels are substantially reduced across the after-treatment system. Engine out hydrocarbons were much higher from the low subcycle, again, which includes the cold start emissions, as would be expected. In terms of fuel effects, the low density fuels reduce engine out hydrocarbons. Benefits are proportionally larger in the low cycle results. B30 tends to reduce engine out hydrocarbons. Cetane number improver increases the benefit, so much as was observed for carbon monoxide. Benefits are proportionally larger in the whole cycle results, so again a trend which is seen with carbon monoxide. And now to conclude. So from these WLTC tests of 6 drop-in diesel fuels, it can be concluded that low density hydrocarbon fuels can offer benefits in tank to wheel CO2, in other greenhouse gas emissions, and emissions impacting local air quality. Conversely, some traditional benefits of fuel quality on emissions are reduced or even deleted in the tailpipe emissions of cars using advanced exhaust after treatment. Paraffinic diesel fuel as a blend component can give disproportionately large emission benefits, and this bodes well for cases where paraffinic diesel fuels are in short supply, and bodes well for the future when BTL and PTL fuels become more widely available. Advanced after-treatment systems suppress the negative NOx effects associated with the use of high FAME content fuels, and this opens up the door to the use of such fuels in markets which are dominated by advanced vehicles, and that can enable the increased use of such renewables without local air quality drawbacks. In these cars tested, high levels of cetane number improver didn't mitigate the NOx penalty traditionally associated with the use of high FAME content fuels, as reported in California with heavy-duty vehicles. Deleterious fuel effects weren't evident in the emissions slated for future regulation. Small particles and ammonia, for example. However, there were some additional benefits which might be achieved from the application of specific fuel qualities, and they were in the case of methane and nitrous oxide in this study. Most of the fuels tested constitute options to increase renewable fuels, as well as the beneficial tank-to-wheel effects. But additional OEM certification would be required to enable these fuels to be deployed generally in the European market. So I'd like to acknowledge the contributions of the members of Concawe Scientific Task Force 25, which is the diesel fuel and emissions group, Ricardo UK and Corriton Specialty Fuels. I'd like to thank you for accessing this presentation, and if you have any discussion points or questions, please feel free to contact me at rod.williams@shell.com or contact Roland Dauphin at rolanddauphin@concawe.eu. Thanks again for listening. Goodbye.